My name is Angela Zane. I am a rising junior at Newport High School in Washington.
My name is Ray Min. I go to Pineview School for the Gifted in Sarasota, Florida.
My name is Gihao. I'm a rising senior at the Bronx High School of Science in New York.
My name is Ji-yoon, and I'm a rising senior at Lexington High School in Massachusetts.
I'm Arif Chaudhary. I'm a rising senior at Stuyvesant High School in New York.
My name is Wanjun Lee, and I am a rising senior at Bergen County Academies in New Jersey.
My name is Amy D'Angelo, and I'm a rising senior at Independence High School in Frisco, Texas.
I'm Megan, and I'm a rising senior at Lexington High School in Massachusetts.
I'm Alex Du, and I'm a rising senior at the Hotchkiss School in Lakeville, Connecticut.
My name is Shunha Huang. I'm a rising senior at Limerick High School in San Jose Hill.
My name is Rachel Liu, and I'm a rising senior at the Bronx High School of Science in New York.
My name is Edwin Ng. I am a rising senior at Walter Payton High School in Chicago, Illinois.
Hi, I'm Praneeth Moyala, and I'm a rising senior at Thomas Jefferson High School in Alexandria, Virginia.
Hi, I'm Annalise Takashigi, and I am a rising senior at the Bronx High School of Science in New York.
My name is Sadiq Sabor. I'm a rising senior at the Bronx High School of Science in New York.
My name is Vivian, and I'm a rising senior at the Noble and Greenough School in Massachusetts.
My name is Connie, and I'm a rising junior at Weston High School of Massachusetts.
My name is Matthew Song. I'm a rising senior at Westford Academy in Westford, Massachusetts.
My name is Ethan Yen. I'm a rising senior at the Bronx High School of Science in New York.
My name is Evan Ackerman, and I go to the Governor School for Science and Math in South Carolina.
I'm Julian Bain. I'm a rising senior. I go to Hellgate High School in Missoula, Montana.
Hi, I'm Henry Gustis, and I'm a rising senior at Niles West High School in Skokie, Illinois.
My name is Jess, and I'm a rising senior at the Pingree School in New Jersey.
I'm Rebecca Ashmore, and I'm a rising senior from Blackstone Valley Tech in Massachusetts.
My name is Isaac Hubbard. I'm a rising senior at Weston High School in Massachusetts.
My name is Alex Melkoff. I'm a rising senior at Needham High School in Needham, Massachusetts.
My name is Lily Weissman, and I'm a rising senior at Stuyvesant High School in New York.
My name is David McElfresh, and I'm a rising senior at Derry Area High School in Derry, Pennsylvania.
My name is Maya Kushemacher, and I'm a rising sophomore at Carroll High School in Southlake, Texas.
My name is Julian Parker Sochori, and I'm a rising senior at Buckingham Brown and Nichols High School in Cambridge, Massachusetts.
Hi, everybody. We are Team Authy 1, and I'm Anne. We also have Ray, Connie, Praneeth, and Megan.
So we'll first start with a base game overview of how zombies or flu works. So the idea is there is a city that is divided into 9 areas in a 3x3 grid that represents neighborhoods. And in these neighborhoods, there is a chance for a zombie and a flu virus to occur. The goal of this game is to best control the viruses utilizing the deployments, which can either range from quarantines or to firebombs. Obviously, there's RNG involved in the chances and how quickly the rates spread. And to measure this, there is a score metric which will be used to determine how best controlled the city is going. Additionally, there is a fear metric, which is calculated citywide as the average fear per person. There's also a number of each category, including zombie bitten, dead, ashen, zombie, flu infected, and normal.
Okay, so our first mod is the population individuality mod. And as the name implies, we made different NPCs or people in the game have different personalities. Each personality type makes up a different percent of the total city population. And these personality types range from normal, which is considered least extreme, to Karen, to rebel, each characterized by their own actions and behaviors, but also having their own starting levels of fear, trust, and morale. Those 3 attributes change over time to reflect upon the actions taken by people in the game and by the player. So by implementing these components, we made the game experience become richer and more realistic.
So here is our implementation for the attributes in game. So the way that attributes are affected is that different deployments can increase or decrease attributes upon building. And attributes can also passively decrease every turn depending on how many zombies, flu, or dead are in a neighborhood. And the attributes are weighted on a 0 to 100 scale, where 20 is super low, 40 is low, 60 is high, and 80 is super high. So here's our implementation for 2 personalities. And as you can see, the starting attributes are different and the incrementation rates of attributes are also different. So the way that attributes themselves affect the rest of the game, here's an example. High morale can decrease resource costs, while low morale and high fear can increase the cost of resources. So personalities also have special actions. So here's one of them. Karens, rebels, and lunatics are prone to disobeying. And there is also a chance that other NPCs can disobey more or less based on fear or trust levels. So low trust levels or high fear can increase or decrease the chance of disobeying. Here's another special action that can be performed by the rebel. If there is a rebel and there's lower than 20 trust, other super low trust in a neighborhood, there's a chance that that neighborhood can be locked for a turn. And lastly, the nerd personality can increase or change the chance of a cure vaccine working in the neighborhood.
So our second mod is the disease expansion mod. We made a new feature in our game which simulates the ability for viruses to mutate. So there are chances that either or both the flu and zombie viruses can mutate. So when a mutation occurs, the viruses behave in different ways, such as spreading faster or slower, or making vaccines or cures less effective. And this is similar to how diseases spread and change in real life. We also have a quiet cases feature. Quiet cases only occur a very small percent of the time. They include having no zombies at all, having no flu at all, or having neither zombies nor flu in the game. And this is similar to how outbreaks are not always full-blown in real life.
So here's our implementation for the mutations. There are 7 different types of mutations. The faster or slower mutation will decrease or increase the spread of disease. The lethality up or down mutation can increase or decrease the speed of death once you get the disease. Hinder vaccines or cure mutation will make it less likely for a vaccine or cure to successfully work. And the reverse immunity mutation will make it so that any NPC with a immunity for any reason whatsoever will no longer be immune. Every turn, there's a 10% chance of a mutation happening. And from the 7 mutation pool, each mutation can only happen once. We also implemented quiet cases. At the beginning of every game, there is a probability to not have flu or zombies at all, which is 5% for both and 0.25% for both together at the same time.
So this is what the UI looked like with the base game. And for our new UI, it looks like this. And what we did is we added indicators for our variables, including fear, trust, and morale. And we added a small description for each personality to give the player a sense of what to expect. Additionally, we added a reset command so that when they finish the game, they can restart. Also, we added an indication as to whether or not the input they entered is a valid action. Also, the game won't break if it's wrong input, but instead it will ask again. We also added a quality of life improvement in that the location selected will turn red once they're placed to deploy. And finally, we added deployment and location chosen history.
So now we move on to the RL and AI changes that we made. So we basically came up with a new way to calculate score in the game. So we use more specific factors, which makes the way the score is calculated more clear. And they also accurately reflect to what extent we see factors as beneficial or detrimental to the score. In adjusting weights for factors, we made immunity the largest positive factor and zombies the largest negative factor. Additionally, there were some places in the code that we had to change. So we had to expand the state space, which keeps track of the new factors we added. So some deployments cost resources to use. We made that happen. So we track the number of resources used up by the player. And we also track values such as those for the number of healthy or dead people in the game. Finally, we had to expand the observation space too, as expanding the state space directly affects it, and the tracking of new factors there allows for more thorough RL training and more accurate results.
So this is the slide about the data analysis and about the graphs. So basically what we did is that we made a class specifically talking about the human player and the machine player, where the machine player is the AI, and then the human player is just the user. And then we basically had 2 sets of graphs. One graph where it showed the score over time based on the game numbers and the number of times used based on the deployment numbers. And we can compare these 2 sets of graphs to see which one was more effective, the human or the machine. And since we couldn't get real data, we had a few hypotheses on how they should look. And the first one was that the machine player would have a higher overall score than the human with more consistent amounts of increases and fewer downward dips. And the second hypothesis is that the machine player would choose certain deployments more or less often than the human would, which would contribute to their higher score.
And that's the end. Thank you very much for listening to our presentation.
Welcome to Zombie, otherwise known as Zombies or Flu. This game, as previous presentations might have mentioned, puts you in a city of 9 neighborhoods and has you protect innocent civilians from both a zombie outbreak and the flu. You'll have access to various deployments of potential ethical concern and from unknown authorities, but that doesn't matter for now because what we at Team Authy 2 cared about was more that the base game seemed a little lacking, even impractical. To change that, we decided to get to work. Introducing the GUI mod.
So we've been working extremely hard on a GUI that improves upon the original text-based UI, and we think we have developed a GUI that is markedly better in many aspects. So I'm going to have Sadiq bring it up and show it in action while I walk through all the changes. The first thing we changed is how the user selects their actions. Previously, they had to type out the locations and deployments in the terminal, but now they can do so by clicking the buttons on the screen. Also, when the deployments and locations are selected, they show up in the notification bar above. In our opinion, these changes make the gameplay more seamless and removes the need for a keyboard. We also added events, deployments, and actions to the GUI so the user doesn't have to keep track of it. We finally have the data log. If the user has completed at least one turn, they can access it by clicking the notification bar on top. In short, what a data log is a summary that shows all the changes that occurred after a turn. We added this feature because we thought it would allow the user to analyze the situation more quickly and effectively and plan accordingly in the next turn. Or they can use it to revisit past turns. The GUI gives them the option to do so. We also made some minor changes, such as to the stats being displayed on the screen, but I'll hand it over to Sadiq to talk a bit more about it.
So we thought that the statistics in the base game were vague, and unreasonably so. They describe things like population size and zombie count in terms such as none or few or many, and we thought this would be a hindrance in planning effective strategies against the flu and the zombie outbreak, and in real life you would have better statistics. So we implemented numerical statistics. Now, just like real life, these aren't 100% accurate, but we thought that as in real life, statistics that aren't 100% accurate are still workable. We made them still workable in our mod. Our next mod is Events and Interactions, which aims to create more realistic NPC interactions. To create conditions for these interactions, we implemented local fear, which is fear inside each neighborhood based on the deployments deployed there rather than across the whole city. And global fear is now based on the local fears of all the neighborhood. Our first event is gatherings, which occur when the population is high and the fear is low. As you'd imagine with a mass gathering, it increases flu transmission and infection amongst the population, and people have a higher chance to stay closer together and within the neighborhood. Our next event are panics, due to high population and also high fear amongst the population. During a panic, people are much more likely to leave the neighborhood, and also it increases the chance for people to fight back against the zombies. Our third event is swarms, which gives more attention to the zombies themselves and occur when there are at least twice as many zombies as there are people. It gives them a chance to actually destroy player deployments, so players should watch out for that. And it also vastly increases the chance for any alive individual to get bitten by a zombie. Now, we did also do some data analysis on agents playing the game, and so I'll hand it off to Arib for that.
I'll be going over the data we've gathered with our RL agents, though to start off with, I'll have to mention that due to a lack of time, we weren't able to fully train our RL agents, so that's probably had an impact on our results. Moving on to our first thing, we have here deployment usages. In the graph below, you can see the difference in usage for each deployment. Let me restart that. Okay, here we can see a graph of the deployment usage by the RL agent after the mod implementation and before it, comparison between the two over the course of 1,000 games. Our original hypothesis here was that we thought that the RL agent would switch from a more aggressive strategy of firebombing all the zombies and people with flu in order to eliminate them to a more passive strategy of managing fear and removing threats before they appear. We were proven to be correct, as the usage of firebomb barrages had greatly decreased, while the usage of things such as the kiln oversight and the bite center amputate have been increased, with the kiln oversight making sure that dead don't become zombies, and the bite center amputate lowering the chance of becoming zombies. Why these results are significant is that it shows how it is why these results are significant is that it shows the necessity to add more realistic aspects to zombies or flu, as the optimal strategy is shifting from the little changes we did. So even more changes are necessary in order to gather practical data that can be applied to a more realistic real life situation. Moving on to our next graph, we have here a local fear versus score, which shows a scatter plot comparing the local fear average of a game compared to the final score of it. Our original hypothesis here was that a local fear average closer to the point where no events occur would result in the highest possible final score, as we thought the events overall would have a negative impact on it. And we were proven to be right, as the place where no events occur was just the local fear of 20 in our implementation. And as you can see here, there is an increasing trend as you look towards 20. Though our entire system for gathering this data was flawed in a way, what we should have done instead was had a wider zone where no events occur towards the median local fear average, and then had the events occur on opposite sides of that zone. That would have allowed us to gather better data in terms of whether or not it's the panics causing the score to lower the gatherings, or if it's the lack of events that do it. We'd also be able to gather data that could be applied to a more realistic situation, as we could see whether or not keeping citizens extremely fearful of what's happening outside, so much so that they panic, keeping them calm enough that they ignore the situation around and start having gatherings even though there's an ongoing flu outbreak, or if there's a very healthy medium between the two, which would result in the most optimal manner for this. That's all we really have for data analysis currently, since we still need to gather more data, so I'll leave the closing statements off to Sadiq.
This has been Team Afi 2. Thanks for watching our presentation, and we hope you all have a good day.
Hi, we're SGAI Team Chris 1, also known as the Best Team Chris. My name is Junha, and we have Maya, Julian, Amy, Wanjun, and Matthew. We made 4 modifications to the game and updated fear, a sanitation value for each neighborhood, an updated deployment mechanism, and a graphical user interface for the game. The main purpose of our mods is to make the game more realistic and more of a model of real life.
The first mod makes fear less impactful in the game. The original Zombies or Flu game was too heavily influenced by fear, so we reduced the value of fear in 2 ways. The first being having a weighted system, and second, changing the points equation. The result of having a reduced fear value is that the player can care more about saving people than reducing fear, as they should in real life. The first thing we did was assign different weights for the amount of fear added when each deployment is deployed. We created these weights in a config file, so if we notice any weights to be inequitable and require changes, we can simply change the value within this file to set the weights to a different number. We also adjusted the score calculations. Good factors, like active NPCs, have a heavier weight, so the score increases by a lot. Bad factors, like zombie NPCs, will have a much smaller relative weight, so the score will go up very little. The score is the sum of these factors multiplied by their respective NPCs in the city. Now look at the picture all the way on the right. Notice how fear holds very little importance in the score calculations. It originally subtracted 1 times its value, and now only subtracts 0.5 its weight. We also figured that there are many factors that would affect the spread of the flu and zombie viruses throughout a neighborhood that weren't addressed in the original game. These factors include income, sanitation, and population density, all of which are important factors when it comes to modeling disease propagation in a city. We added these factors to our game to better model real life, as this is a serious game. To model income, we had each NPC in the game assigned an income to act as their base salary. To model income distribution, we made there be a 50% chance of being poor, a 30% chance of being normal, and a 20% chance of being wealthy. If you are wealthy, you have a 5% lower chance of getting the flu or becoming a zombie, and if you are poor, you have a 5% higher chance. This models real life, as the more money you have, the more money you can spend on sanitation and security measures. To model population density, we just multiplied the number of people alive by 9, then divided the number of people in the neighborhood. Population density does not affect anything directly, but it is a factor in sanitation levels. Now, to model sanitation, we took the average income of a neighborhood and divided by the population density. Then we multiplied that number by a scalar to make the sanitation level more understandable to the user. Sanitation then goes on to affect the fumes, cough, and mutate probabilities. The higher the sanitation level is in a neighborhood, there is a lower probability of the flu spreading in that neighborhood, as a highly sanitized neighborhood in real life would likely spread the flu less.
So we also added some functionalities to the deployments in the game. So we added 5 new deployments listed at the bottom, the first picture here. And we thought we would add more deployments so that it would model the real world better, where the decision makers have more deployments to use. We can also add and remove deployments, shown in the second picture. And also with that, we created an input validation sequence so that the user can't remove any invalid deployments or non-existing deployments. So also, deployments are affected by the state of the game. For example, a very high fear would decrease the predictability of that deployment. In other words, when fear is high, it's harder to guess how your actions will impact the city, since the people act more irrationally.
These mods to the game mechanics mostly work in the back end to make the model more realistic. To ensure that the user could intuitively play the game, we created a graphical user interface for the user to play the game with. A good UI is crucial for the user to better understand the game and be more likely to play the game.
So this is the graphical UI that we have developed for our game. On the left, I have put the 3x3 tables to show descriptions of each cities and use multiple colors to visualize the data in more appealing ways. We also believe that few non-descriptions was not easy for users to understand, so we have added pie charts to visualize the data. I've also added a graph as the users had difficulty understanding the progress of the game and their past actions. These added features of graphs and charts helped users play the game more quickly and intelligently.
So on the right side of the UI, we decided to keep a lot of the information we were presenting in the base game, but make it a little bit easier to understand and more sequential. And so on the right side of the left side, we included the key for the deployments and locations, so the user knows what to type into the input boxes, and then made it easy for the user to select whether they wanted to add or remove deployments. Additionally, we added a quit button to allow the user to exit out of the UI at any time.
To ensure that these mods had a positive effect on gameplay and modeled accurately, we developed a machine learning agent to learn how to play the game. Data visualization is the main feature here, since it helps us gain insight into how the player, whether it be a machine or a human, is interacting with the game.
So we're going to play this video demonstration of a live visual update of the game states while the RL is training. So right now it's only set to train for 1,000 steps. This agent has no prior training. There are 2 graphs, one for the types of NPCs in the game and one for the score update. The graphs are being updated every game that the agent runs through. So it doesn't look like it's making much progress at all. But let's take a look at the result. So here I'm going to show you the agent that was just trained in the last video actually played the game. Remember, it was only trained for 1,000 steps, which is not a lot. It's not doing too well, which is to be expected. The score has improved a little bit though. Improvements in score are measured by the slope of the score and not the actual value. So a very steep slope is a good thing and a flatter one is a bad thing. Let's take a look at how it performs after 2.5 million iterations. So 2.5 billion steps later, we finally let the machine actually play the game. Then I played the game myself and we compare the performance. The machine's on the left and I am on the right. If you look at the score chart, the machine did very well in the beginning, but I ended up getting a higher score over time. I'd also like to mention that this is just one of the results of the machine's gameplay. We ran it many times with this trained model, and we were surprised every time by what we saw. Here we can see which deployments that the agent likes to use. We let it play 35 times and plotted a histogram of its actions. In practicality, this can help us determine which actions are generally helpful and which ones are not. But more interestingly, in the next visualization, we can see exactly when it used a particular development during each step of the games it played. This visualization is very interesting because combined with the previous data, we might be able to see how the machine responded to different situations during gameplay. Of course, this is on a very small scale, only 35 games, but given more time and resources, we could definitely scale this up. We could train our agent for millions more steps, and we could have it run for thousands more games. Visualization is a powerful tool. It's a window into what the machine is doing, how it trains, and helps us make better decisions. And in gaining insight into its actions, we might even be able to teach it one day.
So thank you so much for listening. We were Team Chris 1, the best Team Chris, and hope you like our modification of the game.
All right, we are Chris 2 the Future, the Christening. My name is Isaac Hubbard. My team members are Beck Ashmore, Henry Gussis, Jess Yetvitsky, Kihao Chen, and Vivian Tao. And our mod is the Neighborhood Diversity mod. Picture this. You're the mayor of a city, and a new threat has emerged, the zombie virus. And as well, an old friend comes to battle, the mighty influenza. As the mayor, you'll need to best allocate deployments such as a flu vaccine clinic, a broadcast system, or even a firebomb barrage to save the city from being overrun. However, people are not all the same. People are different. How can you possibly protect the city with different people? Introducing the Neighborhood Diversity mod. By having different traits between neighborhoods, our mod will be more accurate to reality. We built it around our research question. Which neighborhood would require the most government assistance during an outbreak? We anticipated that the wealthiest neighborhood would require the least assistance, while the most impoverished neighborhood would require the most. Additionally, the initial state of each game is also randomized, leading to more complex and varied strategies game to game. This allows for proper analysis of strategies to find the best plan for a real-world crisis. We implemented this by adding individual traits to the neighborhoods and people, which can change the likelihood of zombie and flu transitions and can also influence movement and other characteristics. For example, the wealthy neighborhood is more isolated and is harder to get into or out of. We also added a nicer user interface to increase player engagement and tweak the scoring algorithm to allow for better analysis. The results so far are that the traits themselves don't end up slowing the virus much. However, gameplay strategies can make use of them in other ways. Our AI's best strategy, for instance, is to use specific deployments to bring all the zombies and flu patients into the wealthy neighborhood, since, as I said, it's more difficult to get in or out. It then keeps them there until the end of the game, then firebombs them all at the end. Overall, our mod revamps the game entirely to allow for better and more specific analysis of our research question. With this analysis, we were able to come up with a concrete strategy, and although our AI was unable to save everyone, it had a strategy that could prevent the outbreak from escalating further. And thus, our advice to a mayor in this situation happens to be the same as our team's motto. If it's not up to our standards, we redefine our standards. After all, it is just a game. A serious game. Thank you.
Hello, we are Team Chris 3. I'm Jiyun and my teammates are Alex, Angela, and Evan. We are implementing a mod that closely represents the fluctuating trust levels of the city people. Here's a quick rundown of how the zombie or flu game works. The user places protective buildings, which shape how the active people, zombies, zombie-bitten, sickly, dead, and dead ashen act. The user executes various actions to minimize the death or infection of people and maximize the final score. So our trust mod is meant to maximize realism in the modeling of disease propagation. Imagine you're the mayor of the city, where new outbreaks of the flu and zombieism arise daily. Of course, citizens will look to you to step up and take authoritative action to ensure their safety. This is precisely the reason why we have added the element of trust between the public and the government. First, we added new buildings that would allow the user more control over the constantly changing trust of the city people. As you can see from this section of our code, each of the 3 new buildings directly affect the trust level of the neighborhood in which they were deployed. The spies are meant to be deployed in neighborhoods that rebel against the mayor when their trust level is dangerously low. When there's a rebellion, the user cannot deploy buildings in that neighborhood unless it is a spy deployment. Now let's look at changes in trust.
The trust for each neighborhood will be an integer between the range of 0 and 100 with 5 different levels. The different trust levels will affect both the NPC's actions and the data displayed to the players. The accuracy of the data is based on their trust. A high level of trust means that the NPCs are more willing to tell the truth. The true data is hidden within a range that is displayed on screen, which widens as trust decreases. If the neighborhood is in rebellion, all data will be displayed as 0 unless a spy is deployed. Higher trust also means that the NPCs will be less hostile, whereas lower trust means that they will be more likely to fight. Now for our randomly generated events. For our randomly generated event scenarios, we have weather, crime, and natural disasters. The types of weathers are sunny, rainy, cloudy, and snowy, which affects the probability of the transitions. For example, in the sunny weather, people are more likely to get bitten because they're outside more. Crime and natural disasters are similar because they are both an unlikely event, and they will significantly lower trust in each neighborhood. Most will also decrease resources to symbolize properties being damaged in real life.
We refer to resources as millions of dollars because it's accurate to the scale of a city. Some buildings produce resources, some cost resources, and others do not affect resources. The passive production of money is dependent on the number of active people in the entire city. The more active people, the higher the net income is. So it's in the user's favor to keep the city people safe and alive so that more money is generated for further deployments.
For the UI, we tried to make the ZOF game feel more immersive so that the player will make more realistic decisions. In the background, we have our city, with 9 clickable neighborhoods in the middle. Pressing the neighborhoods allows the player to see more neighborhood-specific information, such as the amount of zombies and sickly in the neighborhood. Here, a player can place deployments to take their move. At the top, city information is shown, as well as a help button for tutorial purposes and an end turn button to end the current turn and begin the next one.
And here's a short snippet of our game mod in the text-based game.
So a large part of our game modification is our GUI, or graphical user interface. The original game uses a text-based CLI format, which can make it particularly difficult for the user, thereby not really giving us as good of data. Pictured above is a code snippet of our main file for the GUI. This specific piece of code is our central method that listens for user changes, which ends up updating the user interface. We've also implemented a help menu, which is designed for the user to gain vital information concerning the game on screen. And we've also implemented a drop-down menu for the player to choose their deployments.
In this chart, you can see the strategy I've named the police state, which was discovered by our first few fully trained reinforcement learning agents, trained at 1 million steps. Although our ZOF game contains 27 different deployments, the AI consistently used those 2 in this and many other runs. This is most likely because of a weakness in our game where deployment buffs and debuffs remain constant, which makes discovering the best one very easy. Besides this, the scoring function valued trust extremely highly, which is why the police state strategy was born, as don't panic broadcasts and police stations can erase trust in a neighborhood. In this table, we changed how the game scores trust in zombies and trained lots of agents at 1 million steps to determine what are the best deployments depending on what the mayor views as important and unimportant. For example, if the mayor cares more about protecting his people from zombies and flu than his re-election, vaccinations and grouping people together seemed to work very well. For the strategy column, I tried to name a real-life equivalent of placing those deployments. As you may notice, the majority of the results rely heavily on the people being forced to obey the mayor. Although you may at first question this finding, many would argue the reason why COVID has been so difficult for America was because of all the freedoms we have.
Thank you.
Hi, I'm Alex, and we're Team A3. My teammates are David, Lily, Julian, and Rachel, and our mod is called Trust Issues. Trust Issues introduces simulations of social behavior not present in the original ZOF. The mod implements a new trust factor, along with changes to deployments, the user interface, and the scoring mechanism. So what exactly is trust? The diagram you see here shows a large part of how trust works in our mod. So the original ZOF includes fear, which measures how much people fear the authorities. Trust will measure how much people actually trust each other. Whereas fear is global, trust is calculated within individual neighborhoods. Fear can also affect trust by setting a cap for it. So as you'll see, trust can range from 0 to 30, and we've set up different bins. So depending on your trust value, you could be in a different bin in each neighborhood. And depending on your global fear, the highest bin you can reach changes, and you can note that on the right with the max bin part. So as an example, if your fear is within 0 to 10, you could have the max amount of trust at 30, but let's say your fear is within 31 to 40, the max amount of trust you could have would be 21. Like the way the fear cap works, trust also influences NPC movement and transition rates based on these different trust bins. So lower trust makes it more likely for an NPC to stay in a neighborhood, whereas higher trust makes it more likely for an NPC to leave a neighborhood. Similarly, depending on each neighborhood's trust bin, the game either increases or decreases the cough, bite, devour, and fight back rates using these different weights that we've labeled here. We included these features for realism's sake. As people lose trust in each other, they become more inclined to stay home and to stay away from other people. In addition to changing in-game mechanics, trust can fluctuate too, based on the numbers of different NPCs in a neighborhood. So if you note the trust in each neighborhood here, if I take a turn of doing nothing, you'll notice that trust has now changed after one turn. So as the number of zombies and sick people increases, trust decreases. And as zombies and sick people become less abundant, trust increases. We included this feature to allow for balancing levels of trust, and to make these fluctuations more realistic, we also allowed trust to change by a small amount in adjacent neighborhoods. Despite this presence of a balancing system, we don't want trust to be fluctuating arbitrarily. We want players to actually have some control over trust levels. So certain deployments can increase or decrease trust, with the most influential one being the new media building that you see here. We'll talk about that in a second. This relationship also works the other way around. Trust can affect certain buildings. So buildings that restrict movement, like the quarantine, become more effective with lower trust levels. And buildings that call for human action, such as the rally point, become less effective with lower trust levels. The last thing we did to even further simulate social behavior was create 2 social groups. At the start of the game, each person is randomly assigned one of these 2 groups, and each neighborhood keeps track of which group holds the majority of people. So you can see that here where it says majority group. When the game decides movement for each NPC, members of the majority will be more likely to stay, and members of the minority will be more likely to leave a neighborhood. Furthermore, the 2 zombie cure stations and the 2 flu vaccine buildings hold less of an effect on whether that's negative or positive on NPCs of the minority in a neighborhood. We included all these features to simulate different biases that stem from racism, ableism, or xenophobia. We want trust to affect the user's final score, thus the user receives a penalty for decreased amounts of trust and a reward for increased amounts of trust. And this encourages the player to improve trust levels in each neighborhood. As mentioned previously, we want players to have control over trust levels, and so one of our new deployments, the media buildings, satisfy this. The optimistic media building increases trust by 4 every turn, and the pessimistic media building decreases trust by 4 every turn. We also added a new building called the testing facility. These buildings affect the accuracy of reports in each neighborhood, and so you can see that with the few, none. You could also have many. Those are the 3 levels in the original ZOF. With a government distributed testing facility, your levels can now be very few or some. So all the 5 now could be none, very few, some, or many in that order. The fraudulent testing facility, on the other hand, doesn't actually show these masked reports. However, it shows actual numbers. Yet these numbers have a very high chance of being inaccurate, whether that's by a small or large amount. This makes the building risky to use, but still viable for certain strategies. In addition to these two new deployments, we made some slight changes to existing mechanisms. So you can now remove buildings from a neighborhood, and so I can do that here if I remove the fraudulent testing facility I just added. Now it's gone. Deployment, we have a deployment cap of 5 in each neighborhood, so players can't just add tons and tons of buildings to a single neighborhood. And barrage firebombs now destroy all buildings in a neighborhood, so I can show that here. So that's all for buildings and social behavior. Rachel will now talk about UI and score.
We also made changes to the existing UI features and also added our own new features. Neighborhoods now display the deployment in them, as you can see in the display. And this makes the game easier to play because the players are no longer responsible for keeping track of which deployments are in which neighborhood. The deployment table also now shows which deployments affect fear, resources, or trust. If a deployment influences one of those 3 factors, a color-coded arrow either pointing up or pointing for increase or down for decrease is displayed next to the deployment name or an ID, and the keys on the bottom showing what each color means. The mod also introduces a new help command that the player could use when prompted for deployment ID every turn. If the player types in help after building ID when prompted to place a deployment, the game will print out a brief summary of the deployment's effects. We also improved the ending screen of the original game because we wanted to add meaning to the user's final actions. This makes it easier for the user to understand the gravity of their actions, and it also encourages them to search for more effective strategies so they could increase their high score. Finally, the final changes we made in our mod revolve around the scoring system. We changed the scoring algorithm to both encourage the user to further contain the zombie or flu spread and to account for the other features added in our mod. As Alex explained, when discussing social behavior, trust now affects the final score, and resources also now influence the score. To prevent the user from doing nothing the whole game, we made it so that the resources don't provide an extremely high reward, and zombies now result in a higher score penalty. All in all, the user is tasked with maintaining a balance between all the aspects of the serious game to achieve the highest score.
So that's all for our mod trust issues. We hope you enjoyed listening. Thank you.
From serious games with AI, I learned how to train an agent using reinforcement learning and how to implement it into our game.
From serious games with AI, I learned about different commands in command prompt and in Python.
In serious gaming with AI, I learned how to use GitHub and how to utilize my team members' code.
I learned from SGAI how to see through the perspective of a user while developing our game mods.
From serious games with AI, I learned about managing project tasks with Kanban boards.
One thing I learned from SGAI is how to collaborate with other programmers using Git and Kanban board.
One thing I learned with serious games and AI is data visualization with reinforcement learning.
In serious games with AI, I learned the importance of understanding your goals and creating manageable, well-organized tasks for your team and for yourself in order to better achieve your goals.
One thing I learned from SGAI is that communication and collaboration are key for good product development.
In serious games with AI, I learned how to design games with an experimental purpose, as well as how to effectively manage work through Agile.
During my time attending SGAI, I learned about the significance of teamwork and communication for project management and the role of reinforcement learning in serious games.
Through serious games with AI, I've learned more about the collaborative aspect of any software and product development process.
From serious games and AI, I learned how Git works and how it functions with GitHub.
From my experience in serious games with AI, I took away a lot about organizing tasks and time management with the use of Kanban boards.
From SGAI, I learned approaches to software development like Agile.
SGAI, I learned about the importance of daily Scrum and team transparency.
In serious games with AI, I learned the significance of collaborating and communicating with the team in the process of software development through using GitHub and Kanban boards.
In serious games with AI, I learned about collaborative programming using Agile, Kanban boards, and Git.
In SGAI, I learned the importance of good communication habits when using GitHub and Trello. From SGAI, I learned artificial intelligence implementation in Python.
In serious games with AI, I've learned a lot about how to most effectively communicate and work with the team on a coding project.
From SGAI, I learned about how to develop a game's UI, as well as how to use Python.
In SGAI, I learned how to collaborate on code effectively with others using GitHub and Trello.
As part of SGAI, I learned a lot about organization and project management techniques, which I'd not known before.
SGAI, I learned how to write and train machine learning algorithms with Python.
One thing I learned in serious games with AI was how to use advanced Python modules such as NumPy and Matplotlib to analyze data.
SGAI has taught me a lot about the collaborative programming process, including the use of GitHub and agile practices.
One thing I learned in serious games with AI is how to collaborate with people from all over the country only through a computer.
From SGAI, I've learned how to better manage work and divide it among team members using a Kanban board.
From serious games with AI, I learned how to effectively communicate and work together with a team remotely.